So that's why the Sith are very obviously better than the Jedi. Awesome. Okay, 2.4, we are leaving the traditional sense of numbers, and just a heads up, this does tie in with the zeros of polynomials, which is really the big focus that we've been kind of skirting around this whole time, whether it's a quadratic or we're dividing to find them, whatever the case might be. This is halfway through the section, which means following 2.4, what should we expect? Woohoo! Yeah, it's a quiz. All right. So, for today, we are going to jump into the world, and this is going to be redundant, so I'm just going to write it right here. We are going to be talking today, at first, we're going to define for ourselves the complex numbers. I would like to never have to write this word again. You guys know several number sets. The real numbers is a blackboard R. The rational numbers is a blackboard Q for quotient. Let's see other ones we have. The integers are a Z. I wish I could get a good reason for you, and so forth and so on. Anybody remember the complexes? What do you think it starts with? It's a blackboard C, which just means it's a capital C with a bar through it. The complex numbers are that fancy C. This is a blackboard C, just like we use blackboard R for the real numbers. Okay. Now, as we go through here, we need to make two little statements. And I think these are recall. And they seem to be because you guys remembered a bunch of this stuff. If I asked you to solve this equation, how would you go through it? You might notice it's a binomial, but it's not what? Crickets is not the right answer. It's not, what do you mean? Okay, so you're absolutely right. What I was looking for is it's not a difference of squares. So we can't use x minus 1, x plus 1 here. This is a sum of squares. Now, Rafa suggested to solve this then, maybe what we should do is subtract 1 from each side and obtain x squared is then equal to negative 1, or it'd be negative 1. And then we would take the square root of this. I'll do the left side. It's x. When we introduce the square root of a number, we add the plus or minus, and it's the square root of negative 1. Now, up until today, this has not existed. And actually, you guys knew it existed, I think. But we essentially work over the real numbers most of the time in here. So this is one of the things that broke us in the real numbers. What is this number? Plus or minus I. Now, I have a gripe with this. We use the letter I for this when we're talking about complex numbers. This number I hate the language. I stands for what? Imaginary, which makes you think that these maybe don't exist or they're less real. And I hate the language. It's terrible. We can call them whatever other type of numbers. I'll tell you, the philosophy of mathematics, in my opinion, is an interesting topic. But the real universe, like when physics gets crazy and you start talking about like why does the universe actually work the way it is, these sorts of numbers are much more impactful and really ingrained within reality than other types of numbers. Imaginary is a terrible choice. Okay, their existence is equally valid to the real numbers, to the integers, and all those. Awful choice of words. Now, as we look at these, that was a quick recall. We're just going to jump right in, and we're going to define these after the recall. So this looks odd, but here we go. When we talk about the complex numbers, these, we're going to make it really mathy. We are going to let A and B belong to the set of or be in the set of real numbers. Remember, that's that fancy notation. A and B are real numbers. Then, a number is complex, and I would just use that blackboard C if I were you, in standard form if it can be written and I'm going to just pause for dramatic effect. It is a complex number if it can be written a plus bi. This is a complex number. Now, as we go through here, couple little comments that we want to make. All of our number systems are just containing smaller number systems. So for example, if I look at the real numbers, which is all the decimals and all the integers are just a smaller section of the real numbers, right? And those are positives and negatives. If I then restrict my integers to not have any negatives and only have zeros, we get a smaller number set called the whole numbers. Do it again, we take out 0 and you get the natural numbers. They're all just smaller parts of a larger piece. It turns out that the real numbers aren't the end. Like, that's not the top level. The top level is these complex numbers. And we're going to make two quick statements. If b happens to be equal to 0, then this complex number can be specified more cleanly. Then this is, and I'm going to say it, referring to the number. If b is 0, like, let's just think of it, 500 million plus 0i. Did I really have to include 0i? Do you guys agree it was just 500 million? And there's no imaginary part to it. This is real. If b is 0, which literally every number you've ever written, think of a number, add 0i. It's been complex all along. Okay, but there's another option. b could be 0, but a could also be 0. If a happens to be 0, we have what is known as a pure imaginary number. Bless you. And again, hate the language. Initially, it was quaternions was the language that was used. The quaternions, which is a specific thing. Bless you. Okay. Everybody cool with that? All right. As we start going through it, there's something that always throws people off with this. I wasn't your Algebra 2 teacher, so I don't know how well you did this. If I ever write an autobiography, here is a little subsection, but this is what I would call it. We and I want you and us to consider the powers of I, which I think is an awesome name for an autobiography for somebody who teaches math, just for the record. My life's not cool enough to write a book about, but if it were, okay. Here's what I want us to think of, and I want you guys to play around with this. We're going to make a loop. Okay, here's what I want us to think. I to the 1 happens. I want us to consider what happens when we do I to the 2, I to the 3, and I to the 4. Now, I'm going to help us with the first part because it might seem odd that it does this. Have you guys ever seen this before? Maybe last year you talked about this? Cool. This is knocking on the door of what is called modular arithmetic. It's where you divide and you only count into certain ways. Like, you guys use modular math all the time. 1 p.m., how many numbers on a clock? 12. So the 13th hour of the day, if you go a full circle, is at 1, yeah? Because you just go to 12 and start over. That is a number system based in modulus 12 is what we use for that. So we use mod stuff all the time, and we'll look at that here in a second. But I want to play around with this idea. I to the 1 is just I. Do you guys agree with that? Okay. As we go through here then, I'm going to do some scratch work over here, and we're going to construct this whole loop to see that it works. If I asked again what I to the 1 is, you guys know that it's just I. If I wanted to do I squared, do you guys agree that it's I times I? Make sure you're getting notes somewhere, okay? As we look at this, that doesn't really do anything, though, for me. What's I again? So do you guys agree that this is just root negative 1 times root negative 1? And then we can even go one step further to clean this up. This is simply the square root of negative 1 squared. And we're one step away. I'm about to square a square root. What is it going to leave behind? Negative 1. Okay, I want you guys to do similar scratch work for me here to get me what I cubed and I to the fourth are. I'm going to give you a moment. Talk it out with your neighbors. We're going to make sense of this, and I'm going to start prepping to teach you guys quick modular stuff. Awesome. I'm going to give us like 2 minutes.
One I without the negative.
You did. That's what it was. Okay. Now, a couple tips for you guys. If I told you that 3 to the 5th, and I don't know this number, but I will. If I told you that 3 to the power of 5 time, 3 to the 5, there we go. If I told you that 3 to the power of 5 was 243, don't write this down. If it's in white, don't write. We're just going to go with that as a convention. If I tell you 3 to the 5 is 243, and then I said, oh, now I want you to find 3 to the 6th, would you guys go 3 times 3 times 3 times 3 times 3 times 3 times 3 and do it 6 times? What's the better way to do it?
243 times 3 times 3.
You just take 243, that's 3 to the 5 already, and you multiply it by 3. Yeah. Do you guys agree with that? Let's use that idea here. If I already know that I squared is -1, then to get to I cubed, you just multiply this by I again, right? Which means I cubed is what? -I. Okay, so I'm going to write over here, I cubed equals -I. Which means if I wanted to do I to the 4th for this last one, do you guys agree it's -I times I? Which, what does this give me? Careful, take smaller steps. You're right, just so you know, but take smaller steps. What's -I times I? One step away. -I squared. And hold on though, I squared was what? And all of a sudden we get +1. Now, if I asked you guys, now that we know I to the 4th is 1, I said, what's I to the 5th? It's I again, which means I to the 6th is just -1. And we just get in this loop over and over and over, right? Now, why we're doing this, and I'm pretty sure this is an Algebra 2 idea. You guys have probably seen this. If I asked you real quick, and we're going to do an example, and we'll annotate it here in a second, we are never going to keep I squared in an answer, or I to the cube, or I to the 4th. You're always going to replace them every time. This is part of simplifying with complex numbers. I want you to evaluate the following for me. On example A, I want I to the 217. Let's get crazy. Do you really want to have to loop yourself over and over and over and over? I don't want to have to do this 217 times, but check it out. If your remainder is 0, you just get I to that. So let's think about this for an example. We're going to make a note. To find this, to evaluate, first, take the power divided by, how many steps were there along the way here? 4. Let's take the power divided by 4 and just see what we get. So 217 divided by 4. I know it's not going to go in nicely. Does 4 go into 200? 50 times 5t, I like that. And there's 17 left. Does 4 go into 17? Not nicely. How many times will it fit without perfect? So it's 54 is the number, and it's going to get us to 216. What's the remainder? 1. Now, notice what that means. We went and got 1 out of this answer 54 times. So it's just 1 times 1 times 1, 54 times when you were to break it down. There's how many left over? 1. To evaluate this, we've done the first thing. It's 54 with a remainder of 1. Now, use the remainder as your power. Very specifically, what that means to us is that we have determined that I to the power of 217 is going to be the exact same thing as I to, what was the remainder? To the 1. What's I to the 1? I. You have just divided mod 4. is what this is called. So if we said 217 divided by 4, it is just 1 mod 4. It's the remainder when we divide by 4. That's all that's left. On B, I want you to do one more for me. I want you to evaluate I to the, I don't know, 29th. I lied. It's going to be to the 30. Sorry. There's a possibility that you can do this without showing any work. If you can divide by 4 and keep track of your remainder, you're golden. I'm going to not put my pencil there because people always tend to wait because I like to write stuff fast. Is there a remainder when you do 30 divided by 4?
Yeah.
What's the remainder?
2.
So this is 2 mod 4 is the language we would use, but the remainder is all we need. What's I squared? We done. That easy. Okay. One more, or are we good on that? Because 30 divided by 4 equals 7 remainder of 2. And I'm going to put a box around that because that's the more important part. Yes, Sean? I thought so, but I waited like 3 times to see if it was going to happen. Cool. Another one, are we good? And on we go then. All right, so this idea is nice. Hopefully did that look familiar? You guys talked about mod stuff, or you've at least seen this idea? Cool. Now, the main focus for this section, as we get rolling with it, we're going to move past just the definition. Like we have them defined, that's all fine and dandy. The real focus that we're going to get into is how do we do operations within the complex numbers. So operations in the complex numbers, or that. Now, for these, a couple different options that we're going to stick with. I'm going to try to go fast, and you guys are going to do really good about telling me if it's too fast. The 2 simplest operations are what? Addition, and I'm going to use my apostrophe, addition, and subtraction. There's my made-up pieces. Okay, we're going to do this real general. We're going to try to. If I wanted to add 2 numbers that are both complex, I'm going to say let's take our first one, a plus bi. And then let's say we're adding or subtracting, so I'm going to use plus or minus because it's going to just work either direction. Plus or minus c plus di. And I'm only using different letters to indicate that we have a possibly different complex number. If you got to write the rules for how we added these things together, how would you want it to work? Sean, if you got to say, just gut feeling, you want the answer to be this because it's the way that your brain works, what would you want these to add up to? So I heard this, a plus c plus what? And I think you were right. Just repeat what you said, and I think we'll have it. So other than the BD part, I like it. Because they have to add, right? So straight up, it's real to real, imaginary to imaginary. Now, to account for this plus or minus, is it possible that it was really a minus c instead? Because this could have just been minus, right? The plus or minus is going to sneak inside of each of these. And I will wait until everybody's looking. I'm going to make this very clear. The plus or minus sneaks inside. Okay. This is super easy to do. The only place I'm concerned about people getting goofed up is where I'm concerned like 80% of the time, negatives. Let's do one example and just see how it goes. Let's do 4 minus 2i minus negative 3 plus I. Okay. Do the parentheses matter? Wager. Okay. I need to stop saying K as my transition word. I notice it so frequently. These really, 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 really matter. I'm going to get rid of them, but to do so, I have to do what? I must distribute. So let's do that. I'm going to drop these ones because there's nothing connected. 4 minus 2i. And then do you guys agree that becomes plus 3 minus I? Y'all took Algebra 1 in 8th grade math, which means we have like terms I think we can combine. And it's the same idea. What are the real parts of this? 4 and 3, can you combine those with addition? It's 7. What are the imaginary parts of these numbers? Negative 2i and negative I, can you combine those? It is exactly like you are adding two things with x in them. No different, just treat it as a variable. Need I say more here? All right, beyond that, we're going to leave ourselves a nice place to jump in tomorrow. There's not going to be any homework tonight, unfortunately. What's cooler than addition? That's right, it's multiplication. We are going to write the definition for this today, and then tomorrow at the start of class, we'll just jump right in with examples. Okay, multiplication. This one's going to be ugly if we write it out. I'm going to say the easiest way to think about this is a one-word statement. FOIL! That's it. All you have to do is FOIL, which is a fancy word for saying distribute. All right, I lied. I'm going to give you one little piece of homework. This evening, I want you to do the following. I want you to multiply for me. I'm just going to say mult is the name of the example. We'll do one more at the start of class. I'm going to check this at the start of class tomorrow, just so you know. Do this one problem. I want you to multiply for me 2 minus 4i and 3 plus 3i. Your answer is not allowed to have an I squared, an I cubed, or an I to the 4th, or I to any power left in it except 1. You can have an I, only I, to the 1. Cool. All right. I will. I'm just going to pause it. But thanks for the heads up.